Maybe I'll just sit and do
All
it.
right.
It's fine.
Yeah, you can do it. You can sit down. So, good evening, everybody. Welcome to our last normal TWed of the fall 2018 season. In a couple weeks, we'll have our end of the term lightning talks, which everybody is excited to do. You'll be getting notices about signing up for that shortly. And next week is an Our Pirates meeting up in Amos Eaton. It's a little bit of logistics. Like usual, we are streaming this on the interweb for posterity. And you feel free to ask questions.
Yes.
We're happy to have Neha do our presentation tonight. She's going to be talking about work that she's done in a couple different places. She'll talk through that. And it's when I was looking for volunteers for TWed, she said, "Can I talk about anything I want to?" I want to talk about this. So we're really excited. Part of the purpose of TWed is for us to learn and to understand new things, and this is a very cool topic. So take it away, Neha.
Thank you. Yeah, please feel free to ask questions at any point of time. So the topic for the day is stress and machine learning, and the work was done at Advanced Wireless System Research Center at SUNY Oswego and System Security and Machine Learning Lab at Syracuse University. So before we understand what is the connection between stress and machine learning, let's know the major components of our whole talk. The first thing is stress. Now, many people just listen this word and they are like, oh, it's stress. It has to do something with negative thing, or it has to do something like ill effects or something. But what stress is? Stress is nothing but the way our body responds to every life event that we go through at every moment in our life. And it also helps us it says us whether we should fight or flight. Say, for example, you're in a forest and a lion comes in front of you. Then how do you know what you need to do? That is where stress comes in action. It tells you need to fly from it. And if there's a place or in a situation where you need to stand and you need to fight for yourself, that is also where stress comes into action. And it gives you more strength than you think you have so that you can fight for yourself. Now, as I said, stress is of majorly two different kinds. First is eustress, which happens to us when we are happy, or events like promotion, making new friends, getting a graduate degree, marriage, or going on a vacation, or similar kinds of events. They are termed as eustress because they give us positive energy and they give us motivation to do something new and exciting and helps us to perform better. But on the other end, which mostly people connect to as stress, is the negative feelings or if someone close to you dies, or work issues, or a feeling of getting neglected. If those kind of feelings are there, that creates negative stress, which is de-stress. And that really takes a lot out of you. It gives you anxiety. And if it's a long term, it can create much more trouble and make you a chronic patient. And it can give you a mental and physical problems. And these kind of stresses are outside our coping capabilities. So we know this is nothing but a response our body does for flight or fight. How it is happening? Whenever we are in a situation, as I said, every moment in our life, we undergo some kind of stress, be it good, be it bad, some low amount of stress or high amount of stress. What happens then? These two hormones, adrenaline and cortisol, they get into action. They help us to understand what our body should behave like and what should be its response. Now, it helps us by increasing our heartbeat and stimulating perspirations. And it also helps us to access a tissue repair substance and alters the response of immune system. But if we undergo stress for a long time, it means that our heartbeat is working more than it should be for a longer time, which gives a wrong effect, which is like blood vessels get damaged, or you get hypertension, which can also give you make you at a risk of cardiac arrest. It can also lead to type 2 diabetes and so on and so forth. So when we're talking about stress, it depends from person to person. For some person, an event can be a stressful event, whereas for the other, it might be a joyous stressful event, you can say. So like an example, I love solving maths. So for me, any problem of math can't give me any stress in a like a de-stress manner. But a person who hates maths, even a normal addition algebra problem can make them person go like in a de-stress motion or like anxiety and other stuff. So it depends on person to person, and the level of stress for me, which might be like low, might be high for someone else, and vice versa. So we need to know that how the level of stress differs from person to person, and that is why it is important to make a personalized system which can detect stress based on the level of that person, which is good for that person, and not make a general one. Moreover, what happens and why this system is necessary, because when we are growing up with the same similar kind of stress, our body gets used to it. And even when it is having or facing some kind of stress, our body tries to ignore it, deny that it's in a state of stress. So that is why if we have a system, it can help us to understand that yes, we are under stress, and which can also help us to take care of it and not get into a problem in the future. So the next important part is the electrocardiogram. So this one is a very simple diagram. Forget the wave on the top. What is important here is this heart and how these ECG is made. So this portion over here, the small white portion which I'm pointing with my mouse, is the sinoatrial node, which has the pacemaker cells within it, which actually starts the my heartbeat. So when it says heartbeat should start, that is when these rays comes on. These are the electric charges which is passed, and it comes here. So when this is happening on your left atrial, there's this electrical charge which is made, by which this form of the wave comes in. In the similar fashion, when this rays, like the blood is pumped to the ventricles, and you can see the ventricle size, the mass is so huge. So anyway, whatever signal is passing there will be very evident, and we can see that, okay, this is what is happening. And so all these waves are made by the contraction and expansion of these ventricles and atrials of the heart when it pumps blood. So why I have put these different kinds of heartbeats here? Because this is very important. As we already saw in a previous slide, that whenever a person is in stress, sometimes the heartbeat starts increasing. So if say that is a normal heartbeat, so say you have 60 heartbeats in a minute, when you're in stress, it might happen that it goes faster and now you have 80. So that is how it changes in the same minute. And when it's slow, you can just have 40. So it's really very evident that, okay, this is the different parts. And you see in the irregular heartbeat, there is no pattern which can be matched, or which you can see that the same pattern is happening again and again and again. But there might be some irregular heartbeats where you might have patterns also. So this really tells us something, that if we want to depict which kind of stress level a person is undergoing, and we want to analyze that, we can actually use this as our tool and as a signal, because first thing, these are always unique. So if you take a heartbeat of a person now, and if you take it after 10 minutes or after 6 months or after a year or 10 years, it changes. So in machine learning field and all, it's not very easy, especially in the authentication biometric field, it's not easy to replicate it or to forge it. So whenever we do a research on ECG, there are two basic things that we look into. One is non-fiducial features, which is nothing but this whole heartbeat as a whole, and we use some statistical tools on it, say like mean, median, or any kind of method that we want, but on the whole wave. And the other one is the fiducial features, which are these wave points, the PQRST, which is on the wave. Those are the fiducial features. So when we are working with fiducial features, we can still use the statistics method, but we use it only on those points. So say if I want to have the P to P ratio or the P to P distance, then I'll take the same, so I'll take two consecutive waves and I'll see the distance between P, and that is how I calculate distance and all.
I have a question. So can you use only like a single EKG reading to determine whether a given stress is eustress or the other type of stress, or do you need
No, not just single one. So I'll come to that point. At least 5 seconds of data is required, because in 5 seconds of data, you at least get 5 heartbeats, 4 to 5 heartbeats, which is efficient, or which is like itself okay to detect which level of stress are you undergoing. because you need to know the patterns and the frequency. So with just one heartbeat, it's not evident that what is the heartbeat or how it is changing.
Would it be possible for like two people to have the same EKG reading but be undergoing like different levels of stress qualitatively?
So generally, no two people can have the same ECG. It's always different. But again, if it is possible, which I've not heard of, but still, if it is possible, then it is also possible that both of you are undergoing different level of stresses. That depends on the base ECG that we have collected from you. So if your base ECG and your current ECG is almost the same, then it means that you are not undergoing stress. But for the other person who has the same ECG, their base ECG is different, it means that person is undergoing different kind of stress. So that is why personalized analysis is really very important. Okay. So how do we do that? This is an overall concept of how we can use machine learning. So we get this ECG, we extract features using feature mining. Then we use different classifiers and we work on them and see, we compare them and see which one works best and how we can use which one, because this work was a part of a big work. So we just wanted to know the stepping stone and how we can go ahead. So we tried all the possible ways and how we can do it. And using these classifiers, we can make a personalized wireless stress detection system. Yeah.
So basically, classification is basically to detect the stress, or it's like basically giving you a value of the stress from
No, it's detecting which level of stress are you in. Are you in low stress, medium stress, or high stress?
and like thresholds are the same for everyone. That low, high,
It depends on the individual. So that is why we say personalized over here, because the low threshold for you might be a high threshold for someone else.
how
So
do you
based,
determine those thresholds? Like how do you
we'll come into that. But again, just as a general thing, so it's like if I have to get to know your baseline, that is really important. So we'll just make you sit in a very relaxed environment so that you feel relaxed, and then we calculate your normal ECG, which we call a base ECG. And then based on that, we see how it is differing at every point, which helps us to determine at which level of stress you are. So for the research purpose, we use this data, and this data is a part of the big data set collected at MIT in the media lab by Jennifer Healy for her PhD project. So they had a lot of drivers, and this was done based on they started the experiment at the MIT garage, from where the driver had to take a back reverse drive and then get on the road and then go to highway and city and come back. So they had a lot of drivers, but we just selected these 10 drivers based on the data that they had. Many other drivers, their data were either missing or they were corrupted and full of noise. So we decided to just choose this 10 drivers. And here when you're seeing, what we are doing is, so in the actual data set, they had other sensors also, but we are just focusing on ECG for two purposes: to reduce the computational time and the cost of computation. So for that, if you can just use one signal to detect, it's the best thing because it's faster and more feasible. So over here, so what they say that initial rest and the final rest is considered as a low stress, because you're in the setting where you have meditational song going on and you just sit and relax. And this city 1, city 2, city 3, they are termed as high stress because at MIT when they go out, there are two roads which merge and they make a bottleneck, which creates a lot of stress on the drivers to drive over there, because at every second they have to stop and it's like very busy road. And you might just also take like more than 1 hour to just cross that 1 mile, not even 1 mile, like some fraction of that score. And this highway 1 and highway 2 is considered as medium stress because all these tests and all these driving portions were done in a controlled environment. So the drivers were told that on highway you have to go at this speed and you have to keep on right or left and work accordingly. So that is how it was instructed to them and it was done. So city 1, city 2, city 3 instances are taken as high stress instances. Highway 1, highway 2 is medium, and initial and final rest is the low stress.
on
Yeah.
this chart?
Yeah. This one
Yeah,
or this one?
the table.
Okay.
The first point seems to be off. City 1 drive 05 says like 1600.
Sorry, that's a typo mistake. That should be 16 minutes. So that should be a dot. Yeah. Thank you. Okay. So now we have the data and we need features, right? And because it was a basic work, so we decided to do a brute force method. We know we are using the fiducial points, and as said, like QRS is the best one. So if you remember the figure from here, this P and this T wave, they almost look similar, right? And if a person is in high stress, the frequency increases like uh, a lot, then this P and T wave tends to coincide, and it's difficult to say which is P and which is T. But this QRS is very separate, and you can know, okay, this is QRS. So we just focus on the QRS complex of the ECG wave. So based on that, we extracted these 14 features. And over here, this part, average difference beat, is very important to understand, because that is not any different speed. It is the difference of your low stress and your medium stress, your low stress and your high stress. So that helps us to understand the stress level of an individual. And that came out to be a very important feature in our whole experiment, because the decision tree also first picked this one in the tree hierarchy. So this was really important, because this tells us the difference and how an individual's heartbeat is changing from time to time. And this RR extracted and QQ is like the distance between the R of the heartbeat 1 and R of heartbeat 2. In that way it goes. We used Weka. For people who are not familiar with Weka, it's like a tool where which helps us in machine learning, and we can play with the parameters because it has all the machine learning, mostly, I won't say all, mostly all the machine learning algorithms built in with different sections, and you can play with the parameters and fix them the way you want it. Weka you can do with Java also. So it has 2 versions. But yeah, we use that. And these were the classifiers that I used for the comparative study. And the details of each classifier is mentioned in our paper. And as I said, initial rest and final rest is low stress. So here, because we have to give classes names and all, so we had 3 classes, class 0, 1, and 2. Later, we move on to just 2 classes, because in machine learning, it has seen that it's easier for them to say yes or no, which is binary classification, rather than doing a multi-class classification, even if it's just 3 classes. So this is how we did the assessment. We wanted to do a leave or not cross validation. That is what in general and reality happens. So say a person is there and the system knows about n seconds, and they know the details. So what happens after n plus 1 second, whether the system is able to say whether that person is in stress or not. So I'm saying in second, you can take as that instance that we are taking, either 5 seconds or 10 seconds or 1 minute, whatever that is. So over there, what happens tenfold, if you have 10 instances or say 10 data points, it takes 9 data points as training, and the last one is used as testing. And this keeps on happening for each and every data, and then it averages and gives you the final answer. So that was really important for us. And we had 2-fold, 10-folds, 90 split. It's the same way, like 90% of the whole data is taken as training, and the rest 10 is as testing. Yeah. Yeah.
So just like a very naive question. The basically classifiers that you run need to be done on a per individual basis, right? It cannot be done for the entire patients, because it's basically that.
No, this one we are doing for the whole data set as a whole. So here
at the threshold.
So that is what I'm saying. The average difference speed that we are having, that feature, that helps us to do. So we're not setting a threshold as in over here to say that, okay, below this is this low stress and above this is high stress. Over here, we have these data points, right? Data sets, 1 instance, 2 instance, 3, 4, 5, 6, right? So it should be 5, not 6. So every driver, say, has 5 instances, okay? And we want to know if this instance is in highway 2, so this instance should go in a medium stress only. So because you are doing a class B, right? So we provide this whole data set to our system, and then it classifies which instance is a part of which stress level?
Like basically, this is your supposedly training data.
Yeah, so see, this is my training data. So when I'm doing a leave one out cross validation, it takes all these data, leaves this one out, uses this as a testing data. So it trains on the rest. Say they are like n instances. It trains on the n minus one instance, tests with this nth instance. Then it includes this one into a training one and leaves this one out. So in that way, it leaves each and every one out and then keeps on testing. Okay. Yeah.
So you can at some point talk about validating this against cortisol levels and that sort of thing? Or
Again?
So you mentioned at the very beginning that using cortisol levels is
Individual.
Yeah.
So that we'll be doing when we are doing authentication.
Okay.
So see, even when we're doing the whole way, when it's personalizing, you know which instance is going. So Weka predicts and tells you that this instance was originally from this person and at this level. Now it has gone to this person and this level. So Weka tells you in their output, if you do the prediction output. So in that way, you can match and see it. Or else you can also, there's a correlation matrix and all, which you can see and see, okay, how it is happening. But here, the first thing that we wanted to do is whether our system can actually classify stress level as separate stress levels. So if it can do that, then we can go to the next level. Yeah. So when we did on the 3 classes and the first 8 features, then we did not get a very good result, but it was not even bad because this was like, according to our knowledge, this was like one of the very few studies where we just use ECG to detect stress, because till date researchers said that they had to use some other sensors also with ECG to get nice above 80% or 90% accuracy. So with that also, when we were getting like 85.71%, we were like, okay, we can do some kind, but we need to work on it, because currently we are doing a very brute force method, very naive method, and using everything that we have, and we have not done any feature like selection or any other process over here. But the important thing was we had like 0 false positive rate and 0 false negative rate, especially for dysentery, which was really nice, because if there is no false positive and false negative, it means there's something good that is happening and you can work on that. Okay. So because you're not getting that good results in 3 classes, and as we said, machine learnings are much better for 2 classes because it loves to say yes or no, rather than asking him to say maybe. So that is why we did just 2 classes. And in 2 classes, we used a very nice thing. We just took the low stress and the high stress, so that they are 2 very distinct stresses. And there's no medium stress, which can just create trouble for the machine to understand. So we just took the low stress and the high stress, and we reran the whole experiment, the same setting, the same experiments. And now we saw that our results just increased a lot. So we thought maybe there's some biasness or something that we need to look into, because what is happening. But then we saw that, remember the important feature which I said, the average difference speed. So that really helped us to understand what is happening, because when you're in low stress and when you're high stress, your stress, and we are looking at the frequency of the QRS in a minute or something. So in that way, if in your normal heartbeat rate is 60, it goes to like 100 or 110. So it's very easy for the system to understand whether this one is in the low stress or in the high stress. So because our analysis said that average difference week was really very important, so this time we just said leave around all the other 13 features that we have. Just take one feature, that is average difference week, and see what happens. Because we saw most of the algorithms, they were first picking this particular feature to start their classifications. And when we did this, we actually saw that J48 is the same, because they always used this feature to classify the stress levels. But rest of the other classifiers also increase. If you just compare this one with the previous one, we see they are more like knife just gave 100% in all kind of things. So that was really interesting for us, and we asked different people who are much more experienced in this or experts in this domain to help us out why is this happening? And they said because of this feature, which really helps them to understand and how numerically it can go. So in that way, it is really good.
What's the data set again? MIT data?
MIT data set.
All of these results are from that?
Yes, all of are from there.
How many data points?
So for our work, we just had this much. We had 50, and then we divided them into minutes, 1 minute, 10 minutes, and we had different thing. But I'm not explaining all those because that is available in the paper. But here I'm just trying to do a overview. But I can explain more as and when required. So yeah, as I already discussed these points. So for us, it was very interesting point because till date, whenever they had, even by getting low percentage of accuracy with 3 classes, it was much better than what previous researchers said. Because most of the papers said that it can't be done using only ECG and something or the other. So, but then we saw that it is possible to differentiate between 3 different levels of stresses. And if we just take 2 stress levels, then it's really very good. And the other reason to why exclude the highway data points and just take the low and high one was because in that data set, the highway data points were not very nice. And I personally contacted Jennifer Healy to understand what they are doing and how it is done. And I read her thesis and I had a talk with her. So they had some trouble in capturing the data points in the highway. So that made sense why it had such a lot of noise and why many data points are missing from that particular sections. So yeah, and it was also clear that yes, just using ECG alone, we can detect stress in a person. But over here, as we saw, the data points, like the whole data instance, if I take just one instance, it varied from 7 minutes to 15 minutes as it was quoted in the table. We wanted to know how less time do we need to detect a stress in a person. So for that, the first thing, so we did a temporal analysis over here. So in this, what we did, we were looking again into data. So by this time, I had a talk with Jennifer Healy and I knew what is happening. And they told that all these drivers which were there, all of them were not unique drivers. But in our first study, we did not require them to be unique. We just wanted to know what is the stress level. Whether it's the same person or a different person, that doesn't matter to us. And here what we wanted to do is, what is the minimum time required? So we took 5 minutes of each section for 5 drivers whose data points were the best out of every other drivers that we had. And just based on the data points that we had, the noise level and the outliers and all, we decided the 5 drivers, and I'll show you the data set that we used. And we divided, so we had 5 minutes for each. So we had a total of 25 data points, a big data points. We divided each 5 minutes data set into 60, 30, 20, 15, 10, and 5 seconds. And we did not go below 5 seconds because then they might just have 1 point or 2 point, which will not make sense to for an analysis. So yeah, and again over here, because in the previous one, we had got to know that machine is working better for 2 low and high. So we thought just to know how less it happens for the same models and the same experiment method, we stick to low and high. And because anyway, highway data are not that accurate that we can work on them. So we took like these points. So those 5 to 10 is the minutes from 5 minute to 10 minute was the data that we took for that driver. So all those, and we kept the same name as it was in the data set, so that it's easier for us to map and also check what is happening. So we did that. And again, IR is initial rest, FR is the final rest, C1, C2, C3 are the city 1, city 2, and city 3. So the first and the last column represents the low stress and the medium ones represent the high stress. So this is our new data set now, but this is a subset of the original data set. So we are not changing the data set at any point. It's the same data set, but we are just refining the data that we want based on the data and the quality of data present. And here what we saw was, so in the presentation, I'm just putting the result of 5 minutes and 5 seconds. The rest we have put in this book chapter. So over here, so that ROC is the curve area, which was important. So this work was done when I was in Syracuse University, and in the system security lab, ROC plays a vital role along with accuracy, because accuracy can be biased a lot of time. So it's area under the curve. So when a machine learning algorithm makes some decision, there's always, you can find an area within what is happening, like false positive and false negative, what is the area and how it is happening. So based on that, we get that ROC level over there. But I will double check and then let you know.
Oh, you mean, what does it actually stand for?
Yeah.
It's like receiver
operating characteristic.
Yeah, it's goes back to like the war.
Yeah.
It goes to the original how it originated. The whole notion gets used for area under curve.
Yes. But they write it as ROC because of the original term that is there. But nowadays it is taken as area under curve.
Yeah.
And that's really important in system security system. So yeah, this time we jotted down the ROC and the accuracy percentage together, because this is always useful for the analysis and see how whether your data, whether your results are biased or not, and how accurate your results can be. So yeah, when we did this, so we can see that level of stress is detected, and it's like 84.8% accuracy, which is the highest way that we are getting using J48 and R. But ROC, which is important, we are getting 0.7421. So when we check on net, after 0.75, it's a very nice ROC. So it means your results are better. But over here, 1 minute is not important for us, because when a person goes to a physician to get a checkup or get to know whether the person is in stress or not, physician needs 1 minute to check it, because they have their own way to see by your physical, actions and all. So if a physician can do it in 1 minute, then there's no point for the system to have there if he is doing in the 1 minute only. So I'm just skipping the other results. This is for 5 seconds. And we see the 5 second is increased to 88. So, yeah. So it says that if we have 1 minute data point or we have 5 second data point, the system is really able to classify whether the stress instance that is coming belongs to the low stress or high stress. So, and this, then we also check manually for each instance how many data points they have and how it is working. And before discarding the data points below 5 seconds, we also tried on 1 or 2 of them. And then we saw that it is just 1 or 2 data points. And we went back to the literature to see why is it happening. And based on the way the heartbeat is generated and it happens, so we came to a conclusion that yes, we should just stick to 5 seconds. And the explanation we have given in this chapter why we stick to 5 seconds and all. So this is a comparison graph that we made. So all these different bars are actually for the different time instances from 1 minute to 5 seconds. So like 60 seconds, 45, 30, 15, 10, and 5. And be it training set 1-fold, 2-fold, or 10-fold, we see that in every place, this starts from 60 seconds and this is the 5 seconds. So at every test experiment, we see that 5 seconds is either giving the same amount, like the same accuracy level, or a better accuracy level. So we can say that yes, this like 5 seconds data is really helpful, and it increased from like 2 to 4% accuracy from 60 seconds results that we got.
You mean like 5 seconds duration of data, or
yes, 5 seconds duration.
Or basically 5 seconds from the time that someone was driving?
No. So initially, remember we said that I'm taking 5 minutes of data for each individual from each time thing. So that 5 minutes is divided into different instances. So 1 minute is divided. 1 minute now has 12 instances. So this 5 minutes, if I'm dividing in 5 seconds, I'll have like almost 1,000 something. Mm-hmm. So that total.
So you're saying
so my one instance is
most important.
Yes. 5 seconds data is enough. Because we were doing temporal analysis, so we divided the whole data. Like we had a 15-minute data. We divided them. We just took 5-minute data of that 15-minute data, and we divided that 5-minute data into 5 seconds each.
Which
so we had
you take, like beginning or the end, or the
this ones which I showed you.
So you take 5 minutes of each of the classes.
Yes, from each. So 5 minutes from the initial rest, 5 minutes from city 1, 5 minutes from city 2, 5 minutes from city 3, and 5 minutes from the final rest. These were chosen based on the thesis and the information that we had. So these were the outcomes that we got. But if you see in both these experiments, all the classes were not balanced, bless you, right? And especially in the last one, when we subdivided them into 5-second instances, there was a big, highly imbalanced classes that we had. Because for each individual, we had 10 minutes of low stress and 15 minutes of high stress. So when you divide that into 5 seconds, the ratio of imbalance increases. So we are assuming that if we do a feature selection of all the features that we have, and if we can just balance these classes and then redo our experiments, then maybe the results will have some effect. It might increase, that's our assumption. But now we know that yes, stress can be analyzed, and 5 seconds is enough to detect the level of stress in an individual. Also, because we're just using the QRS complex of an ECG, thus the computational time and the cost of computation decreases. Now the next thing is, can we authenticate? So authentication is a totally different research area where a lot of researchers have tried to authenticate an individual using ECG. But in the starting of my talk, when I said that ECG is unique, and that is why it can be used as a biometric signal, and that is why it's very important in the biometric authentication research area, because it's unique. You can't duplicate it, you can't replicate it. Moreover, if a ECG is in your body, if you're alive, only then you can produce ECG signals. So even when you have fingerprints or iris or something, it can still be used after a person is dead, right? But ECG can't be done. It can't be replayed. So it helps if a system can be built just using ECG. And because ECG changes from stress to stress, so it's more difficult to keep a track and do it. But if a system can be just made using ECG for authentication, it will be almost foolproof. I'll still say almost foolproof because there are ways you can break those systems. There's always ways that you can break those systems. So yeah, so we wanted to see that now. Now, this was the model. So we are using heart rates from here. We know that sinoatrial node and atrials and ventricles and everything. So this is the data that is generating from this heart, right? So this is the actual data of 5 seconds from the data set that we have. That raw data gets annotated, features are extracted, and features are selected. The selected features and the annotated features, sometimes either one or both, goes to a machine learning model. This model then decides, just a minute. This model then decides whether this person whose ECG is coming is the same person or not. Yes.
So basically, one thing which I couldn't understand is like conversion of the waves, temporal data to like basically the features. How is that done? Like basically condensing the 5 minute or like basically 5 second burst of data. How do you figure out those QRS differences and all of that?
So this data was available on PhysioNet. It's the biggest physiological signals collection, and it has, and you can use Segwin and syntax in Segwin to convert these data into annotation forms.
What do you mean like annotation forms?
So say at 1 minute 5 seconds, sorry, at R1 minute 5 and second 10, the user heartbeat was showing was at Q, okay, Q of the QRS complex. So it shows as the open bracket in the file. When it annotates, it annotates in that way. And then if it is R, it annotates as N, and when it is S, it annotates as close parenthesis, okay. And then there are other columns where you can write and you can know, it says that, okay, this is R, this is Q, this is what happened, this is how it was taken. You can do that. So they have this whole system built, which you can use and annotate the signals in the way you want.
That was that list that you had on that one slide, wasn't it? You had a slide on the right-hand slide. You had a whole bunch of different features that were being used.
Yeah, but those features were extracted from the annotated signals.
5 seconds of data. So you mean like
right, 5 seconds or 10 seconds or the whole process as in whole. So we first annotated that signal. sorry, I forgot to say earlier. So that raw signal which comes to us, because we are just extracting QRS, which I showed in the figure. I can show that again. Wait. Okay.
Yeah, that was what I was referring to.
Yeah. So see, those ECG signals are the raw signals, right? We then annotate them. So we have this whole customized program written for it, which uses these raw signals and converts into annotated files the way you want it, and then outputs them into the file the way you want it and in the name. So like you can take the whole signal and the way you like the way I wrote it was automatic. It took like 10 minutes data, and it kept on separating. So the first five, like the first 1 minute we used to go in one file, the next one it will create new files for it, keeps on doing that. So that happens automatically, but you need to understand the whole sequence and the whole physionet and to see which command you want to use exactly and how you want to do it. So like these people have actually worked a lot in building this physionet, and they have all the toolkit available for developers and all. So you can do that. And from those annotated signals, that is when we extract all these features. You have a question, John?
Well, so we got Andreas in the back who's done a lot of shape signature work. It seems like there's another. So what this is doing is pulling out features that are characteristic of the waveform, but they're intervals, different intervals of the waveform.
Yes.
But any given waveform, you can represent that as a polynomial.
Yeah, so that is when you're using a non-fiducial feature. So remember I said you have two ways, fiducial features and non-fiducial features.
Okay.
So when you're doing a polynomial, then you're taking this whole wave and expressing it into a polynomial way, or you're taking some statistical method, right? But I'm using fiducial method. Fiducial method is when I'm just using these points.
Right, I saw, so I get that,
Yeah, so when I have this, so it takes this, okay, so I have multiple forms. So this is QRS, right? So distance between this and this. So if you compare these all graphs over here, you'll see this distance is increasing or decreasing, right?
Right. So I understand it. I guess where I was going, I was kind of in my mind trying to think which would be. Are there any advantages or disadvantages to particular ways to represent it? I mean, it's.
Oh yeah. So researchers have done in both the ways. The best thing that they have saw till date is combination of both.
Oh. Okay.
But whenever they have done this, it's almost like they have other signals also. But because we were just starting and it was a naive time that we were doing and we were understanding, so we just thought to go in one way first and see how it is working, so that we can take further decision in the same way.
Okay.
Any other question? Okay. I'm almost in the last part. I know it's a lot of information, but I'm trying to give as much high level and make it clear. But please ask me questions. So before that, just giving an information of what authentication means. So there is like, we all use our phones every day, right? And why this was important is we know that our phones get hacked every time. We use our laptops and every technological instrument gets hacked now and then. But if those don't use password or don't use any thumbprint or something, but uses our ECG as an authentication process, it makes our life easier. Because we know no one else can get into our system and it's protected, 99.9% it's protected, and we can still work on it being safe, and we can just keep it anywhere. Like there are many people who don't want to keep their phone away from them because they think someone else will take it and they'll hack into the system, right? But this is because it's coming from your own body, it will just detect that. So that is what is happening. We are giving the raw ECG data, and then if the machine learning says that yes, you're the same person. Now I won't go into detail of authentication because it's in a whole area itself where you can do identification or verification. So I'll just say whether that person is the genuine person or not. Say Neha, and I have my laptop. So if the system is built in my laptop, it can say whether the person working on the laptop is Neha or not. Okay. And because we know stress level changes and ECG changes with the stress level, so can the system still authenticate me as Neha when it's trained on one stress level and testing on something else? So, yeah, I'll just say what was the result that we had in this. So we took the same 5 people over there and we did it. So 1 minute instances and 5 minutes. This is the confusion matrix which I was talking about. So just an overview of what confusion matrix is. Confusion matrix takes the individuals that we have on left and on the top, and then if so, okay. So over here, if I have a 1, it means, and this is A, and if say this was also A, then it means yes, it has accurately found the person to be the same person. But if it is not there, it means it has misclassified that person as someone else. And as whom, we know by this. So see over here, this was A, but it was classified as H. It means that 3 instances for user A was identified as user H. So here is where we come as false negative and false positive comes into play. So this really helps us to know. And so in Veka, when you just do like predictions and all, it gives you exactly, it maps it. Like which instance was mapped wrong, and then you can go back and analyze and see why did that happen, so you can work on it. So over here, when we're looking at identification and all, what we see is this is an individual. How many instances did it had, and how many was correctly classified as that individual's instance? Okay, so in that way you know that okay, it is identified or not. So that's one part of authentication where you're identifying that person as the same person based on the instance or the data points applied to the system. So the probability of identifying the individual for us was, and we used 10 subjects, sorry, not 5, was 99. So it was really a very high thing and really important. And we used the same analysis method as it was done by very first researchers in the field, and the method which was accepted by the whole community. So we used the same method to come up with this 99 probability method. And we also saw that because when we see 1 minute instance and 5 minute instance, like this time duration doesn't play a major role in identifying a person. So these were the 2 outcomes, the results that we had. This is just, so last authentication was a part of the poster that I presented in the next conference at Syracuse University, just because it's not available online like this. So I just wanted to show that. And yeah. Thank you.
Very cool. Well, you were gonna, I thought you were gonna say something about the cortisol levels, the salival cortisol levels and stuff, but.
Oh, the adrenaline and cortisol?
Yeah.
Oh, no, I just said that to show that how stress is affecting in this. And
yeah, the reason why I brought that is in one of our classes and also over the summer, we did some work with, that was measuring, partly measuring stress levels and the physiological effects of different kinds of air treatment. Okay, plant wall versus conventional HVAC versus not. And part of the data, in addition to the usual physiological stuff that was being collected, was the cortisol levels and stuff. And the purpose for that was actually the indicator of stress. They were observing, the heart rate effects and of CO2 and all that kind of stuff.
Yeah.
But,
I understand what you're saying, but that's a different research that takes place, and there have been research done on that just based on the cortisol level in a human person, because the more you are stressed or think, you have more cortisol level and adrenaline hormones in your body. But I took that into just to make a connection of, because when we are stressed, these hormones are secreted, which increases heartbeat. So, and that is a main reason why we are using ECG, because that is directly related to the heartbeat.
Right. I guess what I was saying was, I would have thought it could have been used as part of your confirmation that you were indeed getting, getting it, because it's where you think that the increased heart rate is increased in stress. It would be more positive, but it sounds like just a categorization of when things are being measured. That was kind of your positive, was we know that this city driving. These are our representations of stress.
Right.
And so, which is an interesting way to do it. But I also understand that the ultimate purpose was to be able to figure this out. And just the right.
Yeah, I was just trying to complete everything in the Q&A.
No, you did a great job. No.
And I tried to give, like, I could have gone into more details because I can talk on this like for hours and I have no problem with that, but I just tried to concise myself and try to put like some important points, but I'm happy to answer and go into details for any particular part.
Very,
yeah, like that I added just because I wanted to make a connection between stress and why I'm using ECG, because those are really very important thing, and why those heartbeat changes. So to make that clear that yes, that is really very important and can be a big factor to detect which level of stress they are, because that increases only when these hormones are secreted.
So I have a question. So I'm trying to think of I'm trying to envision the practical application of this. Yeah. Okay, so let's use that example of my laptop is going to be ECG.
Right.
Use that. So there's got to be a phase when it's going to learn. It's going to learn me.
Yes.
Okay? And then it's got to learn me with sufficient generality that I can come back. So that John, you got to come back when you're not stressed if you don't log in.
Yeah. So that was one thing. You know what we started this. We were thinking like a person is driving because we are drivers database. So we can say a person is driving. And we know that if that person is in high stress, if he listens to this music, then the person's stress level comes down. So if a person is driving, instead of saying to the person that you are stressed, the system just gives an alert to the music system that play this song, and the song starts playing. So in that way, the stress level comes down. So it was a really very automated thing. And so I have some unpublished work which is under review now, which is working, and where we did much more work on the authentication part and the whole review of ECG and everything. So yeah, we were working on that.
We'll know that if we're in meetings in here, and all of a sudden this music starts. So
that's how you can customize. That's how you can customize your own program, right? Sorry, Rebecca, you were saying something.
No.
No, Sweet Home Alabama is usually the opposite. If that comes out.
No, it's not stress. It means it's happy.
It's a Pavlovian response.
Exactly, it's a happy music. It would bring down your stress. You go, oh, the food is here.
The ringtone on my phone is Sweet Home Alabama. When it rings, that means the pizza's up. And the students are all trained.
So we know that yes, we get up pizzas now.
Other questions? This is pretty cool stuff. Well, let's thank Neha. Wonderful job, Neha. It's too bad there weren't more people, but we have it on the